The angular speed of the magnetic field rotating around the stator is called synchronous speed, ns. To calculate synchronous speed, multiply 120 times the line frequency and then divide by the combined number of north and south stator poles. The table on the right shows the most common synchronous speeds for both 50 Hz and 60 Hz AC line power. Doubling the number of poles will halve the synchronous speed. Except for a special type of AC motor called a synchronous motor, the rotor does not rotate at the synchronous speed. For all AC motors except the synchronous motor, the actual motor speed depends on the motor load, a phenomenon known as slip. You calculate slip as a percentage of the relative angular speed between the rotating magnetic field and the rotor, and then divide by the synchronous speed. Algebraically, slip equals ns minus nr, and then divide by ns, where ns is the synchronous speed and nr is the rotor speed in RPM. Typical slip in AC motors ranges from 0.5% to 8%. Rotor current is proportional to the flux density B in the air gap between the stator and rotor. It is proportional to the slip and to the rotor resistance. Torque induced in the rotor is proportional to the rotor current, which means it is also proportional to the slip. Increasing the load on an AC motor causes it to slow down, thus increasing the slip, the rotor current, and the torque. An AC motor settles at an equilibrium speed when the motor output to the torque equals the load torque. At that point, the motor provides just enough current output to deliver the required torque. Let's look at a typical torque speed curve for an AC induction motor. Locked rotor torque, otherwise known as starting torque, is the torque output of the motor when it's at a standstill. As the motor accelerates, the torque output reduces until it hits the pull-up torque. Then, as speed continues to increase, the torque increases until it peaks at the breakdown torque, sometimes called the pull-out torque. When the motor speed is at 100% of its rated speed, which is less than the synchronous speed by the slip percentage, it produces full load torque. Running an AC motor at the synchronous speed would produce little or no torque, which of course defeats the purpose of buying an AC motor in the first place. The slope of the torque speed curve near the full load torque indicates the degree of speed regulation possible. The flatter the slope, the more that speed can be changed without changing the torque. The National Electrical Manufacturers Association, NEMA or NEMA for short, defines three-phase AC motor designs based on the torque speed curves these motors exhibit and other operational characteristics. For example, you would want design D if you needed a very high startup torque, as motors of these type have much higher startup torque ratings than the other motors. As is typical of many older industries, NEMA created the motor standards over many decades. This occurred as motor manufacturers created custom torque speed curves by altering the motor windings, the rotor slots, the end-ring sizes, rotor bars, and the end-ring resistances. Each type of NEMA motor has a specification on current draw. Per the curve in the slide, the highest current draw is at motor startup, dropping as the motor accelerates to steady-state speed. Startup current is typically 6 to 9 times of operating current. Torque in motors is reduced linearly with nominal voltage input. Per the graph on the right, the entire torque speed curve is pushed down as the nominal voltage input to the motor is reduced. This graph shows current draw as a function of motor power for the NEMA Type B and E motors. The ratio of current at startup to full load current tends to be higher for the smaller NEMA Type B motors. This chart compares all 5 types of NEMA motors for torque, current, slip, and energy efficiency. A few notable conclusions can be drawn from the data. Type D motors have the highest starting torque and are usually used in machines that need it, such as presses, elevators, or lifting equipment. Type E motors have relatively low starting torque, but also low slip and the highest energy efficiency. They are used in applications which need these requirements, such as fans, compressors, and pumps, which tend to be run 24/7. Type A and B motors have low starting torque, but only medium to high energy efficiency. You might want to use one of these for a pump or compressor, which doesn't need to be run 24/7. Type C motors have reasonably high starting torque, but are more energy efficient than Type D motors. Use Type C motors for conveyors, mixing motors, and reciprocating pumps, which need relatively high torque to start, but which run hours lengthy enough to warrant a medium degree of energy efficiency. Let's recap. Now you understand more about the specs for three-phase AC motors. In the next video, we will teach you about two specialized AC induction motors, wire wound and synchronous.